Sure. How are we doing on number one?
So repeat for power total 125. You don't have to like add them to it in the voltage because there's an I and they're added. And why did you use 125? That's just the total power of the whole circuit.
That's the, well, since these things are all parallel to that battery, that's the voltage provided by the battery. So this will be the total voltage. One could also get there from the total current squared times the total resistance. Which also says 138 watts. And then, of course, you could have figured out the power used by each resistor separately and then just added them up. Any surprises? Pretty straightforward. Yeah. Well, go on to number 2 if you're not far along. Similar idea, except this time the resistors are in series.
Would I total be 1?
Nope. Because the current never splits. So whatever current flows through R1 also flows through R2. And also comes out of the battery. I1 and I2 are the same, yes. There's only one current in the entire picture. There's only one path. Any surprises or other questions? Yeah.
For R2, where does the 110 come from?
Okay, on to number 3. Where you get to do everything here. We got all the currents, we got the voltages, we got the total current, and we got our total. So we got A, B, and C done. Questions on A, B, or C? Okay, power by each resistor now. Sure. For what?
Oh, because when you had it on top, you could also
Sure. What do you want to see?
go down.
Down.
Stop. Last step is just a way of double checking that they have some probability of having the right answer. Add up all those powers, should get the total power used, and you can also calculate the total power as I total squared R total. Yeah, sure. Any real surprises? Your circuits won't get any harder than that. And there's almost not too many other permutations one can do with 3 resistors. All right, any other questions? So just a few symbols. That thing with the alternating long and short lines is a battery. The symbols are slightly different sometimes. These are both batteries. All you need, the only thing about a battery is you have alternating long and short lines. Plus, minus. And this thing is a resistor. And then sometimes you'll see it looking a bit weird. You'll have something that looks like this with a resistor with a second pointer coming in like that. And this is called a variable resistor. We won't ever be doing anything. I won't put those on the test, but you might see them in drawings and books and whatnot. Then we have something that looks like this. Looks like a battery, but not. Because it has 2 parallel lines, equal length parallel lines. And this thing is a capacitor. And what they do is store charge and energy. Capacitors store charge, capacitors also store energy. So for resistors, we have Ohm's law. For capacitors, we have this capacitor equation that doesn't get any nice name. Yeah. I don't know.
There's an I.
There's an I there. AC. What is it? TORS. Yeah, there's an I there. IC. Still doesn't look right. Okay. All right. Units of capacitance, by the way, are farad. Sometimes it's all kinds of different things. Mostly it's an F.
capital F for farad. Let's just try one quick calculation with this. Supposing that we have a capacitor and we connect it to our 1.5 volt battery, 1.5 volts, and this capacitor will have a capacitance C is equal to 4.3 millifarads, which would be a very large capacitor, by the way. Then we just want to find the charge. And of course, unscrambling that C equals Q over V equation, you find Q is equal to CV. And so it stores some amount of charge in coulombs. 0.00645 coulombs of charge. And you could think of that as how many electrons? You can convert that to some number of electrons and find out.
You can leave it in millifarad.
Oh, I put it into the 10 to the minus 3 when I put it in the calculator. .03 times 10 to the 16. And how capacitors work is that we have all of our negative charge on one side, and we're missing a whole bunch of charge on the other side. So one side is positive and one side is negative. So on one side you could say we have 4.03 times 10 to the 16th electrons, and on the other side we're missing 4.03 times 10 to the 16th electrons. We have our charge stored. Okay, what is this 1.5 volts? It's the battery. It's also an electric potential difference.
There's too many C's.
Too many C's?
Yeah. There's the Coulomb is C, and then the Farad is C.
Farad's a C. What are you thinking of?
On the first you have C equals Q over F.
Oh, that one. That's Q over V. C is equal to Q over V.
Yeah.
Yeah, if I could just get the speed of light in here, we'd have 3 C's.
Yeah.
Huh? We could do with more symbols, right? Okay, this is the electric potential difference.
And potential difference is not quite potential energy difference, but it's real close to it. Okay. Imagine one of these electrons was actually able to break free of that surface. Why would it want to break free of that surface? Because it wants to get away from its own kind. Perfectly antisocial character. Get away from its own kind. So it breaks free of that surface, and it rushes over to the other side. It crosses that potential difference. So now we have our change in potential energy. It's Q times delta V. And this 1.5 is our delta V. That's the potential difference between these things. So we would say that delta U is equal to, let's put the electron, 1.602 times 10 to the minus 19 coulombs. That's the electron. Times 1.5 volts. And I get 2.4 times 10 to the minus 19 volts. Not volts anymore, it's volts coulombs. Volt coulomb is also known as a joule. And what I'm actually calculating here is just the magnitude of my change in potential energy. So going back to that picture, the electron breaks free of that negative side and runs across to the other side. I'll blow up the picture here a little bit. So here we have a bunch of positives. And here we have a bunch of negatives. And somehow this one manages to get free and heads across because it's attracted to the positives. And we know what the magnitude of its change in potential energy is. It's that 2.4 times 10 to the minus 19 joules. Now the question is, did its potential energy increase or decrease? And the way to think about that thing is, if you let something go and it starts to move, like that, it always decreases its potential energy. So that electron that broke free was able to decrease its potential energy. And where did that potential energy go if it decreased and we believe in energy conservation? Pardon? Into the kinetic energy. And we know how to calculate those kinetic energies. And of course those speeds, right? We've been doing those for a bunch of weeks now. So you can kind of think about this thing as the cathode and the anode. But this is only powered by a 1.5 volt battery, and of course we need 100,000 times that. to get an X-ray.
This piece was,
Scroll up a bit.
so when you said electric potential difference, you're talking about changing potential energy. That doesn't have to do with electric potential difference, right? That was more about the capacitors.
No, they do. This battery of 1.5 volts is electric potential difference. It's the difference between the socket ends of the battery, which the way we have this thing connected in its circuit, that's also the difference between these, essentially the cathode and anode, if you want, this capacitor. And we deal with these numbers as potential difference, but often we're interested in potential energy difference.
But the change in potential energy happens at the capacitor then?
Yeah, if an electron was able to break free and get across, it would gain that potential energy. Well, it would lose that potential energy and gain that kinetic energy. But the big idea is that whenever you're given a potential difference, and since we're dealing with electrons moving across potential differences, that's how you think about its change in potential energy. So as our electrons move from the cathode to the anode, they are losing potential energy and they are gaining kinetic energy. So now if we have, say, this will be the anode. And this will now be 110,000 volts, reasonable for an X-ray tube. We have an electron speeding across. Delta V, 110 kilovolts. And I'm really thinking about that as a magnitude. And then delta U, the magnitude of delta V, of the potential energy difference. And I can talk about the change in potential energy and magnitude being 110 keV. Since I was talking about magnitude, that E is just the fundamental E, or the positive value, 1.602 times 10 to the minus 19. So the electron decreased by 100, its potential energy decreased by 110 keV, and the electron gained 110 keV of kinetic energy. We're probably far better off just putting that in words than trying to put it in symbols and get all the minus signs to come out right. The idea of energy conservation. So what's the difference between kV and kV?
Could you repeat why is 110 kV?
Because this was 110 V. 110,000 V. 110,000 volts. So 110,000 volts becomes 110 kilovolts.
Oh, I meant KeV on the bottom.
K up there is 1,000, K down here is.
K here and K there are both 1,000. The E is that, the charge, because that's an electron. And the V is the same V that's there. Yeah, this is the part that feels a little slippery.
So we have 110,000 volts. Write that as 110,000 kV. Everybody's okay with that, right? kV, rather. This is a voltage. This is an energy.
So it's also 110 kilojoules?
No.
No? Oh, no, you have to convert that.
If you want to express this energy in joules, you have to plug in the E, what the E is, the 1.602 times 10 to the minus 19. And then you can get it in joules. Yeah.
Potential what? Oh, thank you.
Yeah. So, coming out of the wall sockets here, what do we have for a potential difference? Anyone know? 120. And if you happen to be in Japan or Europe, it's not 120, it's 240. It's double. We have 110 volts coming out of the wall. But our X-ray machine needs 110,000 volts. So how do you get from 100 volts to 110,000 volts? Call up PG and say, I need more power. We need something called a transformer, which is kind of where we're going. But in order to get to the transformer, we have to understand something about magnetism next. So we're going to leave circuits for a bit and go off and talk about magnetism. Magnetic forces. We all know what a magnet is. Have we experienced a magnet? Where do you find magnets? On the refrigerator, of course, yes. Do you have any magnets on you? Cell phones aren't particularly magnetic, one hopes. There could be some. Well, yes, there's a small, very tiny little magnet that's in the speaker of your cell phone. There you go. There is a little magnet there. You get that one. You can't have a speaker without a little tiny magnet. The credit cards. A magnetic strip on the back of your credit card, yes, so we find magnets. And of course, you've probably seen this view of the magnet that you've probably seen since somewhere around the 1st or 2nd grade. You've got a north pole and a south pole on your bar magnet. And then somewhere along about the 3rd grade, they sprinkled some iron filings on a metal plate and held it near a magnet, and you saw these lines appear. And you said, oh, these must be magnetic field lines. Kind of like what's going on with that. And if you looked at that picture, you would say, well, okay, the magnetic field lines, they seem to go from north to south. And we could say that they start on the north and they end on the south. But don't say that. We could say it. We don't want to say that. That was fine in the 3rd grade. It's not fine now. Magnetic field lines actually don't end.
So these magnetic field lines, they continue right on through the magnet. But still, there is something kind of compelling about this North Pole, South Pole image, right? There's something different there. If it's not exactly where the field lines end, you can think of the South Pole as where the field lines come together. And you could think of the North Pole as where the field lines go apart. And that's really what we mean by a North Pole and a South Pole. Diverge and converge. And another thing about magnetic field lines, if we had a compass, a small magnetic compass like you would take out in the woods and go for a walk, if you've ever done that, you've probably seen those compasses with the little needles. And what they are is just small magnets, and what they do is they line up with the field. So if I took out one of my small little compasses, and my compass was had a little needle on it, like so, the needle on the compass would be pointing in this direction. And so now we're going to do that on, think about the entire Earth here. And of course here we are at 37 degrees latitude, and we have our little compass needle. And we're holding the compass, and it's pointing in that direction. There's my compass. Not a great drawing, but you kind of get the picture. And we would say, of course, what's happening is that the compass needle is telling me that way to the north, right? That's how we would interpret that direction. Yes? All right. And if we followed that compass needle, it would follow until we get up to someplace in northern Canada where it dives down into the ground. And then it comes back out on the other side of the planet, and there's our field line. So these are the magnetic field lines of the Earth. Now, where the field lines converge, is that a North Pole or a South Pole? Want me to scroll up, yes? Yes, so this is a South magnetic pole. And of course the other end is a North magnetic pole. Because they point towards the South Pole, South magnetic. Yes, it's unfortunately a little sort of a, when that compass needle is pointing north, it's because it's pointing in the direction that the field lines point. So this compass needle is pointing towards a South magnetic pole.
So, geographic North Pole is the magnetic South Pole. And actually those two are not quite lined up, but they're really, really close. At least for the time being. The magnetic poles do change. Slowly over time. We're going to be all-inclusive here. I'm going to write down the source of all magnetic fields. Not just some magnetic fields, but every magnetic field. What is the source of all magnetic fields? Drum roll, please. That would be a fun idea. If gravity can make a charge move, well then yes, it can be thought of as creating a magnetic field. But moving charge is what creates a magnetic field. All moving charge creates a magnetic field. So, back to that credit card. That little plastic strip on the back of your credit card. And the refrigerator magnet. Where are the moving charges? Yeah, we need a moving charge to create a magnetic field. Where are they? I mean, if I thought of a circuit with a battery in it and some kind of resistor, I would say, okay, I know where that moving charge is, right? I would say there's a current here. So there must be a moving charge and there must be a magnetic field. And it's true, all circuits create magnetic fields. It is sometimes, in electrical engineering circles, a bit of a challenge to deal with that. One of the nice things about cable television, if you ever plugged in your cable to your television in the days before we did everything on the internet, when you actually plugged the cable into the TV. Take a look at that wire. It's a special type of wire. It's got a little tiny metal thing in the middle of it, and it's called a coaxial cable. So the idea is to avoid creating magnetic fields as much as possible. So a lot of work goes into that. But our refrigerator magnet and your credit card are not plugged into anything, right? At least not yet. Who knows what Google will do with them eventually. Yeah, so our refrigerator. Here's our nice big Sears refrigerator with our nice big refrigerator magnet on it. North and south. So that thing is not actually plugged into anything, so where is the moving charge? And in your credit card, where is the moving charge? And if I said the atom, you would say, oh yes? It's obvious now? It makes sense. It's all clear. I don't need to say any more. You can explain the rest. Can you?
The electrons.
There you go. See, you don't need me. She's got it all. The electrons in the atom. How do you draw the atom? You got your nucleus. And you got your 3 ellipses. There's your atom. Well, that's a picture of an atom, right? Sure. And these ellipses are supposed to indicate the orbitals in some sense of where the atoms are moving around. So yes, the electrons in the atom are what the moving electrons inside the atom create the magnetic field. But it's not quite that simple, of course. Well, that part is that simple. But how do we get refrigerator magnets? And why is it that certain things are completely, have no magnetic properties whatsoever? It's certainly got atoms. The atoms in this paper certainly have electrons that are spinning, so it's creating magnetic fields. But we certainly never think of paper as being magnetic, right? So there's something different about things like iron in particular and everything else. The symbol for iron, Fe, ferric. Iron has a property that the atoms really like to work together and they accentuate each other's magnetic field. So the atoms in iron particularly and a few other metals really like to work together. The atoms influence each other. They create these things called magnetic domains and they create larger magnets. And of course this is called how to make magnets. They are called lodestone back in ancient Greece and probably even China before that. Chunks of iron that was basically expelled from volcanoes at the time, but they were inside the earth and very hot and also exposed to the earth's magnetic field. Then they're expelled and they cool off. And when they're influenced by a magnetic field and they're hot, then they can line up all their magnetic domains. Then as they cool, if they're still exposed to that magnetic field, their domains stay that way. And you end up with rocks that have this magnetic property. And it was originally called lodestone. Yeah, certainly the ancient Greeks had it, and very probably the Chinese, even before that, had figured out what this ferromagnetism was. So ferromagnetism, we take a little iron magnet and all its atoms are kind of lined up. How can you get rid of its magnetism? Bang it on things. And you can disrupt its magnetism. Heat it up is another way. You can make the magnetic domains line up. So magnets are sensitive to that sort of thing. So this is a strong interaction of the atoms. Okay, so now we go back to my refrigerator and my refrigerator magnet. I still want to know what's going on here. My refrigerator magnet is unfortunately stuck to my refrigerator. And I'm trying to figure out why this works. And I kind of understand how the refrigerator magnet, what it's doing, is that it's creating magnetic field lines that kind of do this sort of thing. And now the question is, what is the refrigerator doing? Is it doing anything? It's standing there.
me blow up this picture a little bit bigger here. So here's my magnet again. North, south. Here's my big old refrigerator. And I said there's a field line coming off the magnet, going back through it, kind of like so. And the refrigerator's doing something. The refrigerator is made out of steel by and large, which is a large component of iron. And if we take a look back at this quick little drawing I made of magnetic field lines passing through magnets, one thing you might decide to say is that the magnetic field lines are closer together in the metal than they are outside of the metal. And they like to be inside iron. In particularly magnetic field lines, they just pass more easily through iron than they do air because the iron responds in this ferromagnetic way. All its atoms line up. So these field lines tend to respond rather nicely. A lot of them just sort of go through here. And you might sort of begin to visualize this big thing as another magnet. And in particular, you would say the magnetic lines are going in there and they're coming out there. So your refrigerator door acts like a magnet lined up the other way. And now this is the other property you've seen about magnets. North pole and south pole attract each other. South pole and north pole attract each other. Magnets stick together that way. So one of the reasons that the magnets do this is to keep their field lines traveling through the iron as much as possible. So if you had north-south, south-north, two different magnets, you can make all the field lines just stay inside iron. And magnetic field lines are a lot happier when they're inside metal, if one could speak in an anthropomorphic sense there. They like to be inside iron. Yeah.
So since they're flipped, the south and the north and north and south for the two, is there like a reverse? You know how they all go in one direction? So it's like the opposite of what it would normally go to? So is there two sort of cycles? Like why is it just one?
In both cases, I mean, you can think of it as leaving the north side and entering the south side. It works the same way here. If you started here, you'd say left and north and went through the south. If you started here, you'd say left and north and went through the south.
You might want to contrast that situation with a situation like so. Let's take north and south. So if you put two magnets next to each other like so, north and north, south and south, and if you try to draw field lines in such a way that, how could you draw these field lines? Couldn't really do a whole lot. You can start on the north here and it can go around like so. That's good. You can start here, but now you got to squeeze in along there. and do this business. And of course, if you did this one here, it'd also be kind of a squeeze in along there. And these two field lines, they would prefer to be farther apart. So that's that repulsive push you feel that when you experience trying to push magnets together in the wrong way. All right. So what's the source of all magnetic fields? Moving charge, right. This happens to be inside the atoms. Now we want to talk just briefly about magnetic forces. So this is a little weird statement here. A moving charged particle, think electron or proton, may experience a force when moving through a magnetic field. Doesn't always experience it, but sometimes it does. And here's our qualification. If the velocity is perpendicular to the field, it will experience a force. So I'm going to have a proton here. I want to start off with positively charged particles. The proton is moving along in this direction. There is a magnetic field going in this direction. By the way, I didn't tell you how we label magnetic fields. The symbol for magnetic field is V. And that is a positive charged particle. And so the question now is, which way is that force on that positively charged particle? And this is a good thing to end on. Make the fingers of your right hand point in the direction of the velocity. It's actually physical thing. You have to use your right hand, make your fingers point in that direction. Fingers of your right hand pointing in that direction. The magnetic field vector is going up. Think of that as coming out of the palm of your hand. And you've got good posture with your thumb. It's not a whole flat thumb. You extend your thumb as a good one. Or think of your fingers as curling in that direction, curling towards the other one. Your thumb is pointing in the direction. It's called the right hand rule. And that force is out of the page by something called the right hand rule. And there's a whole bunch of different versions of these things that we're going to encounter. All right, great place to stop.
Force, like the direction, like I already did it, but I was just wondering, when you label the force, like
The force
one
on.
to another, and it says the direction of force on Q1 due to Q2. So it's on Q1 due to, like I thought it would be going this way in the wording, but like how do you know that it would be going, it's actually what's happening?
Okay, so these are opposite sign charges, and you describe that as an attractive force. So there is a force on Q1 due to Q2 that is coming in towards Q2.
But if it's, so on Q1, when I read on Q1 due to Q2, I was thinking, like what, from Q2, what force from Q2
Yeah, there is going that way, but this one is, Q2 is positive, so it's pulling it that way.
Okay.
Your arrow has got your arrow.
So what would the F labeling be like?
For what?
Would it be, for this question, would it be F? Okay. So the one that you're interested in is the so it'll be from this out the second one to the second one.
There is a force in this direction.
I know.
But when it's 1 due to 2, it's actually
Change the word.
One due to two. That's the positive. Now we got these two. And you must say this is positive. Oh, yep.
and then if it was like that, it was 3 and 4, or if there was like another one.
Yeah. You can keep going and just pick any pair.
We don't get out last week 4, so we won't be there till 4. Okay, fine. I just let you know.
No, take your time. Drama.